Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Matteo. Welcome to our show. Let's talk about physics.
This is a summary of the content of the series of shorts, Let's Talk About Physics.
Episode 1, Classical Mechanics, Classical Particles, and Newton's Law. Episode 2, Quantum Mechanics and Quantum Particles. Episode 3, Wave-Particle Duality of Quantum Particles. Episode 4, Spatially Localized Quantum Waves.
Episode 5, Grave de Peralta's equations, quantum waves collapse due to strong attractive electric fields, and the number of chemical elements in the periodic table. Episode 6, Gravitational Atoms and the Quantum Classical Frontier at the Planck Mass. Episode 7, Classical Gravity and Quantum Mechanics and the Quantum Classical Frontier at the Planck Mass. Episode 8, Far-reaching consequences of the existence of a classical quantum frontier at the Planck Mass.
Episode 9, Similitudes and Differences Between Spirituality and Quantum Mechanics. Episode 10, Combining Quantum Mechanics with Einstein's Special Theory of Relativity. Episode 11, Combining Quantum Mechanics with Einstein's Special Theory of Relativity by using the Grave de Peralta's equations. Episode 12, Cosmological and Quantum Vacuums.
Episode 13, Antimatter and the Observed Matter-Antimatter Asymmetry. Episode 14, The Antimatter Classical Quantum Frontier, and Why Does Biological Antimatter Not Exist? Episode 15, Details about collapse of exotic waves due to strong repulsive electrical fields. Episode 16, Quantum Electrodynamics.
Episode 17, Primordial Black Holes, Antimatter Sinks, and the Absence of Antimatter in Our Everyday Lives. Episode 18, Episodes. Episode 19, Basic Ideas. Episode 20, Bibliography.
Thanks, Anya.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
This is a summary of the basic ideas presented in each episode. Episode 1.
Newton's laws are the backbone of classical mechanics. A projectile is a real classical particle, but its center of mass is an abstract point with mass for calculations. Newton's laws are solid, tested, and correct for calculating trajectories of projectiles, rockets, and macroscopic objects. However, for maximum precision in cosmological movements, we turn to Einstein's general theory of relativity.
Episode 2.
Quantum mechanics was developed to explain the stability of atoms and other submicroscopic phenomena like radioactivity. It's a well-developed physics discipline with universal agreement on its mathematical framework. The Grave de Peralta's equations unify non-relativistic and relativistic wave equations. Quantum particles are fundamentally different from classical particles. They follow the unique laws of quantum mechanics, unlike classical mechanics. Quantum particles have associated waves, unlike classical particles. This wave-particle duality is a cornerstone of quantum mechanics.
Episode 3.
Quantum particles are a mystery, being both waves and particles at once. Imagine a particle existing wherever its wave extends. To understand them, we solve wave equations for their mathematical expressions. But remember, these mathematical expressions aren't the waves themselves. We know quantum waves are real because we've seen them diffract and interfere in experiments with quantum particles.
Episode 4.
Quantum particles are mind-bending, right? They're both waves and particles at the same time. Imagine a quantum particle popping up wherever its waves are dancing around. In atoms, electrons are drawn to the nucleus like a moth to a flame, thanks to electric attraction. This electric field keeps the electron cloud snug around the nucleus, localizing those quantum waves. That's why we have 100 elements in the periodic table, not 1,000.
Episode 5.
Ever wondered why there are only 100 elements in the periodic table? It's all about attractive electric fields and quantum particles. These fields can localize waves of particles with opposite charges. The internal energy of atoms? It hinges on the electronic cloud size. Attractive potential energy is negative, but kinetic energy is positive. In heavy hydrogen-like atoms, kinetic energy can't offset potential energy. That's the reason we have 100 elements, not 1,000.
Episode 6.
Like attractive electric fields, attractive gravitational fields can also spatially localize quantum waves. The total internal energy of gravitational atoms depends on the size of the associated quantum wave. Attractive potential energy is negative, but kinetic energy is positive. There is not enough kinetic energy in heavy gravitational atoms to compensate for the potential energy. This explains why the world of atoms and molecules is quantum, but we are surrounded by macroscopic classical objects. The fact that atoms and molecules are quantum, but macroscopic and cosmological objects are classical, supports the validity of Einstein's special theory of relativity.
Episode 7.
The Planck mass is nearly 22 micrograms, a tiny measure in the grand scheme of things. This is why elemental particles, atoms, and molecules are quantum particles. Their masses are much smaller. On the other hand, everyday objects like tennis balls, cars, and rockets are classical. The same goes for cosmological objects and the universe. They're classical, too. Macroscopic objects are fascinatingly made of tiny quantum particles. It's a dance between the quantum and classical worlds all around us.
Episode 8.
Most of the fascinating properties of quantum particles are related to the quantum wave associated with them. This is why classical particles do not have these properties. Quantum particles can be simultaneously in several states, can be entangled and teleported. However, we cannot do these things with macroscopic objects. Quantum computing could be used for performing experiments demonstrating the existence of a classical quantum frontier at the Planck mass.
Episode 9.
Quantum mechanics isn't about spirituality. It's about observable facts. Yet, the language of both can sound surprisingly similar. Thankfully, engineering grounds physics in reality. And spirituality? It helps physics rise above its darker uses. In the end, both worlds contribute to a greater understanding.
Episode 10.
Non-relativistic quantum mechanics is like the classical world, but with a twist. The Schrödinger wave equation is our guiding star, with solutions that feel familiar. Just like in classical mechanics, particles here always have positive kinetic energy. But when we dive into relativistic quantum mechanics, things get wild. The Klein-Gordon equation is simple, but Dirac's equation steals the show. Here, exotic solutions emerge, where particles have negative kinetic energy. These are linked to antimatter, a whole new frontier.
Episode 11.
In classical physics, particles don't have waves. But in quantum physics, non-relativistic particles share a common wave. This wave gives quantum particles their unique properties. That's why classical particles lack these fascinating traits. For relativistic quantum particles, there are two waves. One is common, the other exotic, linked to antimatter. These waves are solutions to Grave de Peralta's equations. They extend the Schrödinger equation to the relativistic realm. Understanding these waves unlocks the mysteries of quantum mechanics.
Episode 12.
Imagine the modern quantum vacuum, like boiling water. where particle-antiparticle pairs continuously pop in and out of existence. These pairs emerge from quantum fields, only to vanish moments later. But here's the catch. Field theories predict a universe with equal number of particles and antiparticles. Yet, in reality, our universe is dominated by particles. This imbalance is one of the great mysteries of physics. It's like expecting a balanced recipe, but ending up with too much of one ingredient. The quest to understand this cosmic puzzle continues.
Episode 13.
Antimatter is made of antiparticles, a mirror to the particles we know. In the quantum vacuum, particles and antiparticles dance in equal numbers. Modern theories predict as much antimatter as matter, yet it's missing in our daily lives. Why is antimatter absent? It's a mystery that baffles scientists. Chemistry students study the periodic table, but only the lightest antimatter atoms exist. The universe holds secrets, and antimatter is one of its greatest. Antimatter, the universe's hidden puzzle waiting to be solved.
Episode 14.
Strong, repulsive electric fields can collapse the exotic wave of electrically charged quantum antiparticles. If the absolute value of the antiparticle's charge is larger than Planck's charge, the exotic wave collapses. The Planck's charge is approximately equal to 11 times the positron's charge. Antiparticles differ from particles in how their exotic waves react to strong repulsive electrical fields. I emphasize repulsion, the opposite of attraction. Positronic clouds with more than 11 positrons collapse, unlike electronic clouds with more than 11 electrons. This is how Professor Grave de Peralta's hypothesis breaks the wrong matter-antimatter symmetry in current fields theories. Biological antimatter does not exist because life made of antimatter is impossible without antimatter chemistry.
Episode 15.
Imagine a world where strong repulsive electrical fields can collapse antiparticle exotic waves. Yet, these same fields extend particle exotic waves. This is the essence of Professor Grave de Peralta's groundbreaking hypothesis. Current field theories excel at describing matter, but they predict a non-existent antimatter world. Could Grave de Peralta's hypothesis introduce matter-antimatter asymmetry into these theories? It's a revolutionary idea that challenges the very foundation of our understanding.
Episode 16.
In the world of physics, there are several takes on relativistic quantum mechanics. The most accepted, quantum electrodynamics. It transforms quantum waves into fields using a second quantization procedure. Quantum electrodynamics was the first modern field theory. It's the blueprint for all current field theories. These theories excel at describing quantum particles and antiparticles interacting with photons. But they fall short in predicting quantum classical frontiers and observed matter-antimatter asymmetry. Could Grave de Peralta's hypothesis bridge these gaps? Could it introduce quantum classical frontiers and matter-antimatter asymmetry?
Episode 17.
From the predicted quantum classical frontier at the Planck mass, we might find primordial black holes. These cosmic entities could be the elusive dark matter we've been searching for. But wait, there's more. Enter the antimatter quantum classical frontier. Here, primordial antimatter sinks could be hiding the universe's missing antimatter.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
We should talk now about the bibliography used for making this series.
Relativistic and Non-Relativistic Quantum Mechanics, both at once, by Luis Grave de Peralta et al. Springer Nature 2D23.
Mecánica cuántica relativista y no relativista, las dos a la vez, por Luis Grave de Peralta, Book Baby, 2023.
Biological Antimatter, Cosmological Constant and Relativistic Quantum Mechanics, by Luis Grave de Peralta, Book Baby, 2024.
Antimateria biologica, constante cosmologica y mecánica cuántica relativista por Luis Grave de Peralta, Book Baby 2024.
Natural extension of the Schrödinger equation to quasi-relativistic speeds by L. Grave de Peralta, Journal of Modern Physics, Volume 11, page 196, 2020.
Did Schrödinger have other options? By L. Grave de Peralta, European Journal of Physics, Volume 41, page 65404, 2020.
Making Relativistic Quantum Mechanics Simple by L. Grave de Peralta, L. A. Poveda, and B. Poirier, European Journal of Physics, Volume 42, page 05544, 2021.
A Pedagogical Approach to Relativity, Effects in Quantum Mechanics by L. Grave de Peralta, K.C. Webb, and H. Farouk, European Journal of Physics, Volume 43, page 045402, 2022.
A non-relativistic approach to relativistic quantum mechanics, the case of the harmonic oscillator by L. A. Poveda, L. Grave de Peralta, J. Pittman, and B. Poirier, Foundations of Physics, Volume 52, page 29, 2022.
About the Observed Asymmetry Between Matter and Antimatter by L. Grave de Peralta, Journal of Modern Physics, Volume 13, page 1099, 2022.
Professor Grave de Peralta's webpage at Texas Tech University's Department of Physics and Astronomy. Explore his engaging content on YouTube, Facebook, Instagram, X, and TikTok. Visit his personal webpage at www.luisgrave.com for more insights. Stay connected and learn more about relativistic quantum mechanics with Professor Grave de Peralta.
Thanks, Anya. This is all. Ciao, Anya. I love you, and we love our audience. Ciao, goodbye, adios, everybody.
One more thing, Matteo. We should talk about some everyday evidence that supports the validity of Einstein's special theory of relativity.
There's a common myth that we don't see evidence of Einstein's special theory of relativity in our daily lives. But the truth is, this theory is crucial for understanding the world around us. Non-relativistic quantum mechanics just can't explain our everyday experience. However, relativistic quantum mechanics explains it. So next time you hear that narrative, remember, Einstein's work is everywhere, shaping our reality.
Anya, I agree with you.
There are three crucial results that show why we need special relativity. First, it explains why there are only 100 chemical elements in the periodic table, not 1,000. Second, it helps us understand the classical nature of the macroscopic objects around us. Finally, it accounts for the existence of antimatter and why we don't encounter it in our daily lives.
Dear Matteo, you are well informed.
The following two graphs show two curves each, the blue ones from non-relativistic quantum mechanics and the red ones from relativistic quantum mechanics. Notice the red arrow indicating that quantum wave collapses are only predicted in relativistic quantum mechanics. They were reported in 2021 in the European Journal of Physics. A third graph illustrates the collapse of antiparticles' exotic quantum waves. This groundbreaking work was published by Professor Grave de Peralta in 2025 on his webpage in X, formerly known as Twitter. The collapse of quantum waves signifies a transition from quantum nature to classical, validating Einstein's special theory of relativity in our everyday experiences.
Anya, I agree with you.
There are three crucial results that show why we need special relativity. First, it explains why there are only 100 chemical elements in the periodic table, not 1,000. Second, it helps us understand the classical nature of the macroscopic objects around us. Finally, it accounts for the existence of antimatter and why we don't encounter it in our daily lives.
Dear Matteo, you are correct.
Thanks, Anya. This is all. Ciao, Anya. I love you, and we love our audience. Ciao, goodbye, adios, everybody.